Okay, going to be covering 8.3 out of the book called The Integral and Comparison Test. There's a lot of things I'm going to read here. We will eventually get to some examples, but there's a lot to understand visually, conceptually. So let's get started here. So the main idea here is that in 8.2, we pretty much established that we could only find the sum of particular series, right? A geometric or telescopic series. Otherwise, finding the actual sum of an infinite series is difficult. So what we do instead is we just use tests to figure out whether or not a series converges or diverges. And later on, we'll see that that's good enough for what we need to do. So when we start out here, when we're trying to determine the convergence or divergence of a series, one thing we need to understand is that if we have a series, an infinite series, if we add or subtract a finite number of terms, it should have no impact on the actual convergence or divergence of the series. So let me kind of explain to you what I mean by that. Let's say we have a series that goes from 1 to infinity, right? Something here. And so this is just adding up A1 plus A2 plus A3 plus A4, you do one more, A5, forever. Let's say that this converges, okay, that converges to a number. Then if I were to start the sum, let's say at 3 instead, that means I'm really just going to take out the first two and have A3 plus A4 plus forever. Well, that should also converge. Now, it's not converging to the same number that this one did, but we can say it converges because taking away two numbers from the sum will have no impact on whether or not it actually goes to a number. So if we remove a finite number of terms, then it shouldn't affect the convergence. On the other hand, if this diverged instead, right, let's say went off to infinity or something, then taking out two of the terms, since those two terms are finite, again, we should still have divergence because that meant that the rest of them became infinite. So that's what that note's saying, is that when you're looking at a series, removing a finite number of terms has no impact on the convergence or divergence of the series. Okay, so now we get to our first test in this section to help us determine whether or not a series converges or diverges. And it is called the integral test. And I want to try and explain it to you visually first. So just remember back when we were doing improper integrals, okay, earlier in this course. Hold on, let me bring up this thing real quick. There it is, okay. So when we were doing improper integrals in this class, what we had seen is that this integral was basically taking some function starting at 1 and then trying to find the area underneath this function, right, from 1 to infinity. So this keeps going forever. So that's what that meant. Now, this integral test says, suppose we have a continuous function on some interval, right? And hold on, we're getting to the test yet, but suppose we have a continuous function on the interval 1 to infinity. So we have a function that doesn't have any breaks or jumps or anything like that. That it is a positive function. That means that it is all of the function is always above the x-axis, which we have there in that picture. And very important that the function is decreasing. So the function is moving down as we move from left to right. So let's say that we have that. Then our graph would look, this is an example right here of what it could look like, right? Now, right now, this is 1 over x squared, but I could change the power there and it would impact, it would change the function itself. But let's just, go with 1 over x squared to start, okay? What we're going to do is we are going to restrict this function to just the natural numbers. So we're gonna look at 1 over x squared, but we're only gonna look at the natural numbers. So that means we create that sequence of points. So that's a sequence, right, that we studied back in 8.1. It's just the function evaluated at all the positive integers, right? So the blue is the sequence. Now, what we're gonna do is we restrict it to the natural numbers. And then what we're going to do is we're going to make rectangles. So for each of these dots right here, we're going to construct a rectangle that goes out to the left and down. So let me go ahead and do that. Also, let me fill the area underneath that curve. So that kind of pinkish purplish color is the area under the function, but we are going to construct rectangles out of the sequence. So let me just draw it. So from the first point here, I'm going to go up to that first point, and I'm going to construct a rectangle that goes to the right 1 unit and then down. So we know that the area of this, right, the area of that first rectangle, the area of that right there will be the width of it, which is 1 times however tall it is, which is the function's value at 1. And if we plug 1 in here, we would get 1 over 1 squared. So that's 1. So the area of this thing is 1 times 1, which is 1. Okay, now what? Well, let's do that for each point out of the sequence. So I'm going to do that here. There's the next one, then the next one, then the next one. And what you'll notice is that the area of our rectangles, right? The area of all these rectangles, let's say this is rectangle 1, rectangle 2, rectangle 3, rectangle 4. If we take the area of all of those, what we're going to get is that everything, all of these rectangles underneath here, the area of all the rectangles should be less than the integral from 1 to infinity of the function dx. Now, when I say all the rectangles, I mean all the rectangles that I've circled here. We still have this one, right? But this has a finite area, right? This has an area, let's say in this case 1, but this is finite. So this test says, look, if this converges, right? If this converges to a number, right? Then this right here goes to a number, then the area of all the other rectangles has to be smaller. Then this here has to converge to some number. Now these numbers don't have to be the same. We just know that this number is smaller than that one. And then if we take this one area and add it here, right? What we can still say is that this right here is a number, right? So we're using the fact that this improper integral converges to be able to figure out that the sequence, the series, right, which is the sum of the sequence, also converges. So let me clear this out. All right, so it says here that with the exception of the far left rectangle, okay, which has finite area, all of the rectangles are below the graph of the function. Additionally, the area of each rectangle is equal to the value of the sequent at each point, since the width is 1. So each one of these has a width of 1, so the area is really just the height of the rectangle, which is the sequence value. Therefore, if the area below the function converges, then so does the infinite sum of the sequence. So I'm actually going to have the computer do this for us. So here's the function. We're going to go out here, and I have the computer already giving us calculating this improper integral. So it's determining that the area underneath here is 1. Now here comes the sequence. So there's my first rectangle, 1, right? So I take that and now I add to it the next one. Okay, so now I'm adding to it. This is actually a 1. I don't know why the computer did this, but this is 1 squared. Now, when we do it, plug in 2 into this, where you get 1/2 squared, then 1 cubed, 1/3 squared. And so we keep doing this, and I have the computer adding them up, and you can see the sum here. The further I go, this number is converging. Now, again, it's this right here. This right here is the area underneath the function, and our sequence is summing to something bigger. But you have to remember that that includes this one rectangle on the left here. So if we take that area out of this, right, subtract 1 from that, what remains there is the area or the sum of the rectangles underneath the function. And so that's still finite. Notice the 0.64493, that's staying finite no matter how far I go. You can see it's actually, oh, you know what, we're looking at this number here, 1.63. This is actually, if you could do it to infinity, this is what would happen. You see it converges to 1.64493. I'm here, I have the computer doing more and more terms. It just did like the first 50, 60 of them here. So again, this is just to visually verify that the function converged, right, on that interval 1 to infinity, and the sequence is also converging. And that's what the integral test tells us. Okay, that's the first part of the integral test. Now, the next part says we need to consider something else. So let me take this all back. And all right. Now, what if our improper integral, right? What if the integral we're doing is an improper integral that diverges? So what if we were doing the integral from 1 to infinity of 1 over x dx? Well, we did that in class and we determined that this diverges. Okay, this becomes infinite. So think about it. If you go back up to the picture we had up here, if the area underneath this graph, if this is infinite, right? And then we try and add up these rectangles below it, because these rectangles are below this, right? This sum is would be less than infinity, but that doesn't tell us anything, because just if I tell you that all these numbers add up to be something less than infinity, it could still be infinity or it could converge. So it's not really enough for us to be able to determine. So we're going to do something slightly different. So look, I'm going to have this picture here. Here's 1 over x. We know that that diverges on 1 to infinity. So if we look at this area, right, that's infinite. And what we're going to do is something a little different. We're going to do the same thing with the rectangles, but instead of going up to the point and drawing out to the left, we're going to draw out to the right. So here it comes, a rectangle out to the right with a width of 1. So the area of this rectangle is more than the area of the function. And if I keep doing that out to the right, you can see that the sum of the areas of these rectangles should be greater than the sum of the area underneath the curve. So if the area under the curve diverges, so does the series. So that's what this says. Now here I'm going to show you the example with the computer calculating it for us. So here's the original function, 1 over x. Fill it in. The computer's already telling me that this becomes infinite if I do that. Here comes the sequence. The computer's already telling me that it's going to be infinite, but here I'm going to show it to you with the actual sum. So here's the area of the first rectangle, it's 1. And now I'm going to start adding more rectangles. We're at 2, 2.5, 3, and it's starting to grow, but you see how each rectangle is bigger, right? Bigger above the function. So if the function goes to infinity, so does the series. Okay, so let's get our final conclusion here. Let's say we're given a function which is continuous. That means we can draw without picking our pencil. It's positive, which means it's above the x-axis, and it's decreasing, which means it's going down from left to right. Then if the integral from 1 to infinity of that function converges, right? So if we get a finite area underneath that function, then so does this series, where the series that we're using is the function restricted to those positive integers. So if the improper integral converges, so does the series. And then if the improper integral diverges, then so does the series. So how are we going to use this test, right? Like this is the basic idea, but how do we use this actual test? So here's how we do it. If we're given a series, okay, first thing we're going to do is going to convert the sequence, right? This sequence right here, we're going to convert it into a function f. So we're going to convert it from being restricted to the natural numbers to a function of x, where x is a real number. We're going to restrict it to the domain 1 to infinity. We need to make sure it's continuous. We need to make sure it's positive. That means we need to show that the function's above the x-axis or greater than 0. And we need to show it's decreasing. This one's the tricky one. To show a function's decreasing, that means going down from left to right. We have to show that f of a is greater than f of b whenever a is less than b. That's just saying that if you plug in a number a that is bigger than b, so number a would be to the left of b on the number line, then when you plug those values into the function, f of a is above f of b. That could be hard to do. So there's a nicer way to show that a function is decreasing that comes from Cal 1. All we have to show is that the derivative is negative. So remember, if a function's derivative is positive, that means it's going up, and if it's negative, it's going down. So we're just going to use that most of the time to show that it's a decreasing function. Once we know it's continuous, positive, and decreasing, then all we need to do next is evaluate that improper integral. And then whatever happens here, we'll use the integral test to draw a conclusion. So let's take our first example here. Okay, let's take this example. And let's go ahead and use the integral test on this. So a few things to consider first before we do this. Remember that this right here is our a sub n. And so we might want to just do the quick nth term test on that. Just let n go to infinity. And when we do that, we get 0, and that means the test fails. All right, that's if we're trying that nth term test. We always want to kind of think about that first, because if this turned out to be something other than 0, we'd be done. But it goes to 0, which means we don't know anything. Okay, so then we would say, all right, is it harmonic? Well, it's not harmonic. We don't have a constant over linear. The square root is not linear. So it's not harmonic. Telescopic or collapsing? No, because for that we needed like partial fractions or something with logs or something where we create subtractions. Can't do anything here. And so we're pretty much stuck here. So what we'll do is see, maybe we can integrate that. So what we're going to do is we're going to take this, right, this a sub n, and we're going to convert it to a function of x and look at it as the function 1 over the square root of x plus 1. And then we have to, we have to show that it's positive. We have to show that it's, it's continuous. It's continuous on 0, 1. We have to 0 infinity. Oh my gosh, 1 infinity. We have to show that it's positive on 1 infinity. And we have to show that it's decreasing. So to do that on 1 infinity. So to do that, what we're going to do is first show it's continuous. So when we look at this function, the only number that causes any problems for this function is whenever that x plus 1 is less than or equal to 0. In other words, we need, another way of saying that is we need to make sure that this is always greater than 0. So we can't have any negatives under the root, and we can't have 0 down there because then we'll divide by 0. So we need to make sure that whatever's underneath that root is always greater than 0. And so if I just move that 1 to the other side, x must be greater than -1. But the interval we're on is 1 to infinity. So this is fine. We have no problems with anything being undefined. So it's continuous on that interval. Now, is it positive? Well, we look at that. We look at this right here, and we ask ourselves again, is this greater than 0? Well, since we're plugging in numbers between 1 and infinity, we know that this number is going to be positive. And so if we add 1 to it, it's still going to be positive. So we're basically taking 1 over the square root of a positive number, and that should be a positive number, and that is always greater than 0. So yes, that should be okay. And now the tough part is to show it's decreasing. So to do that, all I'm going to do is I'm going to take the derivative of it. So take the derivative of that function. Now it might help if we remember that this function is actually x plus 1 to the -1/2 before we take the derivative, and then just use chain rule. So we have, this is -1/2, x plus 1 to the -3/2. Times the derivative of what's inside, which is just 1, so don't need to do anything there. This is -1 over 2. And then down here, I'm going to rewrite this as the square root of x plus 1 cubed. All right, and so what I want to make sure is that I need to make sure that this is negative, right? Because that would mean that the derivative is negative, which means that the function is decreasing. So can we convince ourselves that this is always negative? Well, if I'm plugging in numbers that are between 1 and infinity, then that means I'm plugging a positive number in right here. And I add 1, that's positive. I cube it, that's positive. I take the square root of that, that's positive. I multiply by 2, that's positive. So I know for sure I have -1 on top and on the bottom a positive number. And that is, in fact, always greater than 0. I mean, sorry, less than 0 because it's a negative number. So I have shown all three of these are true. Okay, so you have to do that for each of these. You have to make sure that you've shown all these things. Then what you do is say, okay, well, now all I have to really investigate is the integral from 1 to infinity of 1 over the square root of x plus 1 dx. Do this improper integral. If this converges, then we've got convergence of the series. If this diverges, we have divergence of the series. So we need to do this. This is an improper integral, so I have to convert it into a limit. I'm going to let t go to infinity, integral 1 to t, and then 1 over the square root of x plus 1 dx. And I'm going to need to figure out the antiderivative of that, so I'm going to do that over here. What's the integral of 1 over the square root of x plus 1 dx? Well, you could just do a basic use of right here. Just replace x plus 1 with x plus 1 with u, then du is dx, and then when you rewrite this integral, it becomes 1 over square root of u du, which is really the integral of u to the negative 1/2 du. And now just use the power rule. So we add 1/2 to that, or add 1 to that, we get a half. We have to put 2 out here, 2u to the half plus c, which means 2 square root of u plus c. But remember that u was x plus 1. So that's our antiderivative. All right, so once we have that, we come back over here. We say, all right, we're going to take this. We're going to have 2 square root of x plus 1. Oh, forgot the limit. Limit t goes to infinity of, okay, the antiderivative, 2 square root of x plus 1, evaluated from 1 to t. And then we plug in, let's plug in t first. If we plug in t, we get 2 square root of t plus 1, minus if we plug in 1 here, we get 2 root 2. And now we let t go to infinity. And notice that if t goes to infinity, this right here will go to infinity. And that means this one is a number. So infinity minus a number, that's going to be an infinite. And that means this diverges. And since that diverges, we can say that the series that we were looking at does the same thing. So therefore, by the integral test, this series of 1 over the square root of n plus 1 diverges. There we go. So a lot involved there. The integral test is nice, but it is a pain in the butt. You got a lot of things you have to show. So that's how we do it. Let's do another example. For the next one, let's see here. All right. All right, so here's the series. Now, it almost looks geometric. If that n wasn't there, like if this is just 1 over e to the n, we could rewrite that as 1 over e to the n, and then that would look a lot like an r to the n, and we could do a geometric. We just have to make this an n minus 1 or something like that, but you can't because you have an n on top, so no good, can't do it. So really, the only other thing is to maybe try the integral test. I mean, it's not harmonic. It's not a constant over linear. It's not telescopic because we don't have any subtractions there. Can't do partial fractions. We should check the nth term, but if you do nth term, just to make sure it doesn't go to something other than 0. If we take the limit of the sequence, you get infinity over infinity. So if you do L'Hopital one time, then you're going to wind up getting 1 over e to the n, and that goes to 0. And so this test fails because you need something other than 0 to say it diverges. So that doesn't help. So here we go. We're going to convert the sequence into a function of x. So we rewrite that as x over e to the x. And we need to make sure that it is continuous, right? So is it continuous on the interval 1 to infinity? Well, we just got to make sure we never like divide by 0 or something like that. And That's impossible to make the denominator 0, so that should be fine. Is it positive on the interval 1 to infinity? Well, the numerator is going to have to be positive, and the denominator, e to any number, is positive, so this should check out. Is it decreasing? This is usually the harder part. Right, so is it decreasing on that interval 1 to infinity? Well, to do that, let's take the derivative. Okay, the derivative of this function, I'm going to do something that will actually be useful in a moment. I'm going to rewrite this as x e to the negative x. I'm going to bring that e to the x up. And then when I take the derivative, I'm going to do a product rule. So the derivative is derivative of x, which is 1 times e to the negative x, plus the derivative of e to the negative x, which is e to the negative x times negative 1. Be careful, you have to take derivative of the negative x up in the exponent, then still times x. And let me see what I can do here. This is e to the negative x minus x e to the negative x. Just to make it a little easier to look at, I'm going to factor out an e to the negative x. That leaves me with 1 minus x. And one more step, let's just drop that e to the x back down to the bottom. All right, so now take a look at things. If you are only allowed to plug values in between 1 and infinity, we know that the denominator will be positive, right? Because e to any number is a positive number. However, if we plug a number that's 1 or bigger, right? When we plug in 1, we get 0 on top. So that's 0. It's not positive or negative, it's 0. But if we plug in like anything past 1, right? 1.1, 1.001 or 2 or 5, then this right here should give us a negative number. So we'll have a negative over a positive, which means that this is less than 0 whenever we go past 1 for x bigger than 1. And that means that, you know, from 1 on, right, it's going to be decreasing, which is what we need. So this checks out. So now it's integral time, right? So we have to do the integral from 1 to infinity of x e to the negative x dx. All right, I'm going to do that on the side over here. We do this first, x e to the negative x dx. I'm going to have to use integration by parts to do this. So my u will be x, my dv will be e to the negative x dx, du will be dx. And then when I integrate here, be careful, it's negative e to the negative x. So now using ultraviolet minus voodoo, we know that this turns into these two multiplied together, which is going to be negative x e to the negative x minus now these two multiplied together. So negative e to the negative x dx. And I can pull the negative out. So we get negative x e to the negative x plus integral e to the negative x dx. And we just did that antiderivative a moment ago, and we know that that's negative e to the negative x. All right, that is our antiderivative plus c. So we need that over here, and we also need a limit. So we have limit t goes to infinity of, okay, let me go ahead and just plug the antiderivative in, negative x e to the negative x minus e to the negative x. We're evaluating that from 1 to t. I don't like the way that looks. What I'm going to do is I'm going to pull a, let's pull a negative e to the negative x out. And that will give me an x plus 1 right there. And then one more thing before I start doing anything else, let me drop that e to the negative x back down. And I'll put the negative out in front of it like that. Want to evaluate that from 1 to t. Okay, so now let's plug in t first. So when we do t in here, we're going to get t plus 1 over negative e to the t. And then minus, when we plug in 1, we get 2 over negative e to the first power. That's just a number. Okay, and then we let t go to infinity. So if I let t go to infinity, I get infinity on top here, infinity on the bottom. So I should be able to do one application of L'Hopital's rule on that. And when I take the derivative of the top here, I get 1. And on the bottom, I just get negative e to the t. All right, and then we still have this over here. And now if I let t go to infinity, this goes to 0. And this goes to negative, and then 2 over negative e, but that together is some number. And that means that this improper integral converges, right, to some number. Now, what does that tell us? If this integral, this improper integral converges, therefore, the original series, what was it, n over e to the n, what we can say is that this converges by the integral test. Now, very important. This converged to a number. We actually know what the number is. This number is actually 2 over e. But that's what the improper integral converges to. And remember, when we did this, we had the function and we had all the rectangles that were underneath it like this. So we know that the area under this is finite, which tells us that the series is finite, but it's not the same number because there's little regions in here that were little gaps between these. And so we're not trying to claim that we know what it converges to. We're just claiming that it does converge to some number. I can say that it's smaller than that. It's smaller than 2 over e. I just don't know exactly what it is. Okay, so that's the second example of the integral test. We'll get back to the notes here. All right, yeah, we're going to move on to the next series. I'm going to just take a quick pause here. Okay, we're now moving on to another series, right? So, you know, we just did a test, all right? We have the integral test, which is kind of involved, and it allows us to determine whether or not a series or converges or diverges, as long as we can do the integral and show its continuous, positive, decreasing, all that. This is another type of series that we need to be able to identify when we look at it, kind of like the geometric, the telescopic, and the harmonic. Those are the three we already know from the previous section, 8.2. So here's a new one that you need to kind of know. It's called a p-series, all right? And what these things look like is sum n equals 1 to infinity of 1 over n to the p, where p is some fixed power. So here are some examples, just so you can see what p-series would look like. So let's say we had like sum n equals 1 to infinity of 1 over n squared. That would be an example of a p-series. Here p would be 2. Another one, n equals 1 to infinity of 1 over the square root of n. That would be a p-series because we could look at this as being n to the half power. So p would be a half. So as long as the n is the base and the power is a fixed number, then we have a p-series. Do not confuse that with this, 1 over 2 to the n. This is not a p-series because the n here is in the exponent. This would be like a 1/2 to the n, and that would be geometric, right? Because that would be like an r. So this is not what we have here. So we have a very simple result when it comes to p-series, and that is if the p is greater than 1, okay? So if that power is greater than 1, this series will converge. If the power is less than or equal to 1, then we'll get divergence. And I'm just going to show you this, okay? I'm not going to go through a proof of this. You're just going to take this kind of on faith. But here's an actual sequence, right? We're using 1 over n squared. So this is this example here. And I'm having the computer add up the terms of the series, and it actually converges, all right? So let me see here. What is going on? It actually converges. So if we add up all these together, we get 1.64493. So it converges to some number. But watch what happens when I change the power. So if I change power to n to the third, still converges to a smaller number. N to the fourth, 9/2. These are all numbers that are bigger than 1. You can see that I'm still getting convergence. All right. Now, what happens if I let that n get smaller and get less than 1? So let's get to 1 first. Here's 3 halves that's still bigger than 1, still get convergence. Let's go to 1 over n. 1 over n. We've seen this before. This is harmonic, right? But the p-series says that if I let this power on the end get smaller than 1, like a half, that's square root, we get infinity here when we add all these up. And if I go smaller, 1, that's x to the 0. That's going to diverge if we add those up. And then here, this is actually, it's kind of hard to see, but this is 1 over n to the negative 1/2. If you bring that up, it's n to the half, and that's the square root of n. Obviously, that diverges because you're adding up things that get bigger and bigger and bigger. So the p-series is pretty clear, pretty easy to use. I mean, it's just, you just look at the number of the power, and if it's bigger than 1, well, you got convergence, and if it's smaller than or equal to 1, you got divergence. All right. Okay, so that brings us to our next test. All right, so we've got the integral test. We did that first. Talked about this real easy series called a p-series, where we can easily determine if it's convergence or divergence. And now we look at this comparison test. So this test is tricky to understand and sometimes tricky to implement. Take some time to get used to. Let me read through it first. All right. It says, if we're given some series, okay, this is the one we're looking at, and we look at the little sequence inside the series, and those are positive. So this only works for positive series. So we look at that and it's positive. And then what we're going to do, if we're trying to figure out if it converges or diverges, what we're going to do is we're going to try and find a similar series, okay, a different series that's similar to this one, where we have a different sequence inside. And again, that sequence needs to be positive. All right, and we're going to compare the two. All right, that's why this is called a comparison test. The important thing is that the series that we choose to compare to, that one we're going to have to come up with out of our own minds. Okay, whatever we use to compare it to, this series, we better know what it does. All right, so we must know what that series does. Does it converge or diverge before we even begin trying to do the test? So, all right, we've got our series that we're starting with. We don't know what it does. And we come up with this new series where we do know what it does. And we're going to compare the two together. Now, there's two cases. The first case, what if the thing we're comparing it to, right, the thing that we came up out of our minds, what if that is a convergent series? Well, in this case, what we're going to need to do is show at the end of this, is really all that you need to do, is you need to show that the sequence of the original series is always smaller. Each sequence piece is smaller than or equal to each sequence of each piece of the sequence that you're comparing it to. Now, let's try and understand what's going on here. All right. So here's an example. Let's say our original series, I'm going to put this down over here. Let's say our original series is the series sum n equals 1 to infinity of 1 over 3 to the n plus n. Okay, this is not geometric. It would almost be geometric if this n wasn't here. That would be geometric, but because it's plus n, it's not geometric. It's not harmonic. It's not telescopic because you can't subtract anything. The integral test, I don't really think I would want to integrate. I don't think that I would really want to integrate this function. That doesn't look like I have a technique of integration that would make that easy. So I'm not really wanting to do integral test here. But I do know this looks a lot like another series. It looks a lot like just the 1 over 3 to the n series. That's geometric, right? That's a geometric series. And it actually, that geometric right there converges, right? It converges. So I know that this geometric converges. Oh, it converges because you can rewrite that as 1/3 to the n, and then r is 1/3, which is less than 1. So it's convergent. So even though this is not, these aren't the same series, this one looks a whole lot like this one. Well, other than that little n there. So I think this is a good thing to compare it to. So the comparison test says this: if this is convergent, right? If this is convergent, which it is, then imagine that each one of these guys, right? Each one of those pieces of the sequence, right? The sequence. What if each one of those in this sequence was smaller than each one of these in that sequence? Then whatever this adds up to be should be smaller than what this adds up to be. So you can see it here. The black is the original sequence. This is 1/3 n, 3 to the n plus n. You can see that the sequence, each one of those dots is below the 1/3 to the n, which is this one. So that red dot's above that one, that one's above that one, that one's above that one. And that happens no matter how far you go out. Okay, no matter how far you go out. And so since the red ones are always above the black ones, and when we add up the red ones, this right here is the series. If we add up the red ones, they converge because it's geometric. We know it converges. Then when we add up all the red ones, it should be bigger than all the black ones added up, which you can tell from the picture here. And so that means the black one has to converge. All right. So that's what the test is saying. It's tough first time you kind of like hear it. It's like you start with something you don't know, you compare it to something you do know. If the thing you do know converges, then you have to show that all the sequence pieces of the first one, the original one, are smaller than the sequence pieces that you're comparing it to. On the other hand, if it's the other way around, if the thing you're comparing it to diverges, then the only thing that would be useful to you is if you can show all the pieces of your sequence are bigger than the one you're comparing it to. If they're bigger, then the sum that you're looking at has to be bigger than the sum of the one you're comparing it to. And if the one you're comparing it to diverges, goes to infinity, then so does your original series. So I'll show you that in a picture right now too. So look at this one here. This is actually, I need to clear this out. So the original series here that we're looking at is n equals 1 to infinity of n cubed over n to the 4th minus 1. You know what? We need to start the series at 2 or else we'll get division by 0. So we start at 2. That's okay. It's just one term. Remember we said finite number of terms doesn't change anything. This right here is the thing we want to know what it does. And the thing is, what do we compare it to, right? Well, when n gets really big, this minus 1 really doesn't make much of a difference, right? It's like, oh, take 1 away from a huge number. It doesn't matter. So this looks a lot like n cubed over n to the 4th. But that's just 1 over n. And we know that's harmonic. So since this is harmonic, it diverges, right? We have divergence here. So if we can somehow show that these pieces are always bigger than these pieces, then the sum of this should be bigger than the sum of this. And since this diverges, that would also have to diverge. You can see it from this picture here. Now keep in mind, the black one is the original one, and the red one is the one we're comparing it to. You can see that our black dots, it's hard to see. Let me see, maybe I can change this. Yeah, you can kind of see there that the black dots are always above the red ones. So it's the pieces of this one are always bigger than the pieces of this one, or the terms of this one are always bigger than terms of that one. So when we add them up, the black sum should be bigger than the red sum. And if the red sum is becoming divergent going to infinity, then the black sum should do the same thing. Okay, that's the general idea. Let's actually do these examples so you can see exactly how this works. So I'm going to go back up to this one. Let's do that one right there. Given this, try and show that it converges or diverges. So here it is. All right, so we're going to try and determine if this converges or diverges. So first thing, nth term test, let n go to infinity there, you get 0, it tells you nothing. I already said it's not geometric, it's not harmonic, it's not telescopic. I don't want to do the integral test on that. So instead, what I'm going to do is I'm going to compare it. So I'm going to do a comparison test. So here's my original series. 1 to infinity. And I'm going to compare it to this series. Because again, that n really doesn't play a big role. When n gets real big, this 3 to the n is like pretty dominant. Now, I don't know what's going to happen here, okay? I don't know what's going to happen. This is just me saying, hey, that looks a lot like this. Let me compare it. But I have to know this. I have to know what this one does. And I know it's geometric. And I know that it will converge. All right. So what do I want to show then? I want to show then, because this other one converges, right? I want to show that the sequence of the original series, each of those pieces must be smaller than or equal to all of the pieces of the other sequence. Okay. I need to show this is true. If I can show that's true, then since this converged, this one will also. So to do this, I just need to do some algebra here. I kind of cross multiply. Y'all know I don't like saying that, but I'm doing that here. And then I'll subtract 3 to the n on both sides. And when I do that, I get 0 is less than or equal to n. And n, remember, is where we're starting and going to infinity. Yeah, that's always bigger than 0. This is true. This is true for all n. So that means that, you know, all the pieces here are always smaller than all the pieces here. And when we add all those up, it goes to a number. So that means when we add all those up, it's going to go to a number. Not the same number, just a number. So we're done. Okay, therefore, the original series converges. 1/3 to the n plus n converges. Now, I'm not going to say by the comparison test because I already told you I was using the comparison test here. All right. All right. Not so bad, huh? Not so bad. All right, let's look at the next one. So we look at this one here. All right, trying to determine if this converges or diverges. So again, it's not geometric, it's not telescopic, it's not harmonic. Integral test, actually, I wouldn't mind doing an integral on that because I see like a basic u sub. You could let u be the bottom, derivative that's the top, right? If these were x's. So I think integral test might work here, but I'm going to try a comparison instead. So I'm going to take this. Notice the sum starts at 2 because we can't have 1 in there. I'm going to compare this, compare it to, so I'm using the comparison test. I'm going to compare it to sum n equals 2 to infinity of, well, we already said that -1 doesn't make much of a difference. So n cubed over n to the 4th, but we already said that that's 1 over n. So that's harmonic and it diverges. By the way, you could also say that this is a p series with p being 1. You could say it's p series with p being 1. And from the notes before, if p is 1, that means we have divergence. So either way, so I've got a divergent series that I'm comparing to. So if I have a divergent series, here's what I need to show. I want to show that all of these guys are always bigger than these guys, right? Because if I add all these up and they become infinite, as long as these are bigger than that, then this will force these to be infinite, or the sum of them to be infinite. So n cubed over n to the 4th minus 1, I need to show that those are always bigger than or equal to 1 over n. And now I'm going to, again, do that little cross multiply again. I get n to the 4th greater than or equal to n to the 4th minus 1. Let's subtract n to the 4th on both sides. I get 0 greater than or equal to -1. And you know what? That's always true. That's it. I'm done. That wasn't bad. Boy, that's better than doing an integral test. I can tell you that. Therefore, the original series what does it do? Well, this one diverged. All these were bigger than those. It must diverge too. So I'll just point something out here. This inequality right here is the most important part of these because you have to get that right? If this diverges, right? If you were to come here and say, oh, I want to show that n cubed over n to the 4th minus 1 is less than or equal to 1 over n, then all you're saying is, look, if these guys are always bigger than those guys, if these add up to be infinity, right? So if we take the sum of those, that's infinite, we know that. That's bigger than or equal to the sum of these, which, well, you won't know because it could be infinite also, or it could be finite. You know nothing, right? But here we're saying if we add these up and it becomes infinite, then we add these up, it has to be greater than infinity. The only way to be greater than infinity is if you are infinity yourself. So these are both infinite. So that inequality is super important. All right, another example, which is a little tricky. This one's a good one though. So look at this one. It looks so much like the previous problem, but it's not. Okay. All right, so let me see. Yeah, all right, let's do it. Actually, take a quick little pause for a minute here. All right, so this example is pretty interesting. All right, so it looks so much like the last problem with one exception. We have a plus here instead of a minus. So that means we can start at 1, and that's no big deal. We're going to do the comparison. Right, we're going to take this series. And let's compare it to the n cubed over n to the 4th again, because that's really kind of what it looks like. N cubed over n to the 4th, n equals 1 to infinity. And that's just 1 over n, right? So harmonic, right? Diverges. So what do we need to show? Well, we want to show that these guys always stay bigger than these guys, because these are going to sum up to be infinite. So we want that to blow up also. So we want to show that n cubed over n to the 4th plus 1 is bigger than or equal to 1 over n. And when we do our cross multiply this time we get n to the 4th bigger than or equal to n to the 4th plus 1. And if we subtract from both sides, we get 0 is bigger than or equal to 1. And this is not true. So what does that mean? This does not mean, okay, this is where students mess up. This does not mean that this converges, all right? It does not mean this converges. It just means that the comparison test, this comparison didn't work. We were trying to compare it to a divergent series and we came up with this. We tried to show this, but it's not true. So that means something is wrong here. Like we can't do it, right? Maybe we picked the wrong thing to compare it to, but how do we fix this, right? So here's the way that I like to look at it. If you look at the inequality right here, the thing that causes the problem here is that the end of the 4ths goes away. And when that happens, the left-hand side becomes a 0. The right-hand side is 1, the left-hand side becomes a 0. We got the right-hand side of this by doing the multiplication of here to here. So that right there, we don't have any control over. What we can control, though, is how we got the left side, which was this times this. That was our end of the 4th. What we'd like is for it to be where when we bring this end of the 4th over, that we don't get a 0. So something we could do that'd be really clever here is instead of comparing this to 1 over n, what if this was a 2n? Then this would have become 2n cubed, and then this would be 2n to the 4th. And then when we subtract on both sides, we get n to the 4th is bigger than 1, which is true. So I'm going to make a slight adjustment. I'm going to do this over, okay? I'm going to compare this to 1 over 2n. Now, this is still harmonic because it's still a constant over a linear. So I know that it still diverges. So now I'm just going to run through this, even though I just showed it. I'm going to run through this again. I want to show that that's bigger than or equal to 1 over 2n instead, right? And now when I do my cross multiply, I get 2n to the 4th bigger than or equal to n to the 4th plus 1. Subtract n to the 4th on both sides, I get n to the 4th bigger than or equal to 1. And this is true whenever n, because remember, n starts at 1. So this is true. And since that's true, whatever this series does, that does. So therefore, the original series diverges. Clever, huh? We have to be kind of paying attention to what went wrong when we tried it with 1 over n. Pay attention to it and then fix it by adjusting this. Okay, now just to show you, what if you would have been thinking, oh, you know, when we were here at that inequality, you know, what if you were like, okay, one way I could do this instead of the 2n, what if you were thinking, oh, well, I could do n to the second power, and then when I cross multiply, I get n to the fifth bigger than or equal to n to the fourth plus 1. And then you can bring the n to the fourth over. This time you can't subtract them, but you can factor out an n to the fourth and get n minus 1 bigger than or equal to 1. This should be true. If n is going to be 1 or bigger, this number right here should be bigger than 1. So at n equals 1, you'll get 0, but it doesn't have to happen. It doesn't have to happen the whole time. It just has to happen eventually and continue to hold. So if n is 2, notice you'll get right here, you'll get 1, and then over there you'll get 2 to the fourth. That's 16 times 1. That's bigger than 1. And if n is 3, it's going to be even bigger and bigger and bigger. So this will hold eventually. So you might be like, oh, well, why not just use 1 over n squared instead of 1 over 2n? Well, here's the reason you can't do it. Because 1 over n squared, that in here is no longer harmonic. That's now converging, right? It's a p-series. So that means your inequality would have to have flipped over. And then if you do that, this is not true, okay? So you have to be extremely careful with this. Practice will get you used to it. Those are the only examples I'm going to do for this. We're going to move on. So let's take a look now at the next test, all right? All right, we're going to get kind of towards the end of this section here. The last test out of this section is called the limit comparison test. So it's really just a slight adaptation of what we were just doing. You know, in the previous test, what we had was, you know, we started with some series. We came up with a new series to compare it to. We needed to know what that series did. And then depending on what the one we compared it to did, right? We had two cases, either converged or diverged. That would determine what inequality we needed to show, one way or the other. The limit comparison makes this actually a little bit easier. What it does is it says that we're going to start with some series, okay? Still have to have positive terms in the series. We're going to compare it to some other series that has to have positive terms. And we need to know what it does, right? We need to know what that one we're comparing it to does. But we don't have to do the inequalities. All we have to do is take the limit as n goes to infinity of this sequence divided by this sequence. So the ratio of the sequences. Now, if we take this limit and we get a positive constant, so we get a number when we take that limit, like let's say 1 or 2 or negative, or sorry, not negative 5, something like that. As long as it's not infinite, as long as it's a positive number, so it can't be infinity and it can't be 0. If we get a positive constant, then whatever one of the series does, the other series must do the same thing. So if we were comparing it to a convergent series, then we take this limit, we get a positive number, then they both converge. If we started by comparing it to a divergent series and then we take this limit and get a positive constant, then they both diverge. So it's really a nice test. Okay, so like I said, you got to get a positive constant. Can't be infinity, can't be 0. All right. So to do this, all I'm going to do is just do the same problems we just did. Okay, so I'm going to go back and do these 3 problems that we just did, and take this one and do it again using the limit comparison instead of the comparison. So I'm going to start with this series, all right? I'm not going to write it down again. Here's what I'm going to compare it to. I'm going to compare it to 1 over 3 to the n. N equals 1 to infinity. This is geometric. It converges. Okay, so same thing as we did before, but no more inequalities. Here's what I'm going to do. Take the limit as n goes to infinity of this sequence, 1 over 3 to the n plus n, over this sequence, 1 over 3 to the n. And then I'm going to see what happens. So first thing, I'm going to just do some algebra. I'm going to flip that fraction on the bottom up and multiply across. When I do that, I get 3 to the n over 3 to the n plus n. And now when I take this limit, I get infinity over infinity. So I'm going to apply L'Hopital's rule once. And the derivative of 3 to the n, I'm treating it like 3 to the x. Okay, you have to remember, you can't really take derivatives of sequences with L'Hopital, but we already said in class, like, we're going to do it even though we realize it's not technically what we're doing. We're cheating a little bit. We're just skipping the step of changing everything over to x and then back to n. So when you take derivative of 3 to the n, we get itself times natural log of 3. That's cal1. Remember that derivative. And then the bottom, 3 to the n times natural log of 3 plus the derivative of n, which is 1. Okay, now here we kind of the same problem. This is going to infinity over infinity plus 1. So I'm going to do L'Hopital one more time. And when I do that on the top, remember natural log of 3 is a constant, so just ignore it for now. Take derivative of 3 to the n, which is 3 to the n natural log 3. Then you had the natural log 3 that was already there, over. Then we take derivative of this again, which is just what we had up top. And then plus the derivative of 1, which is 0. So we get this. Those are identical. So this is 1. And that is equal to a positive constant. And that means that whatever one of them does, they both do. And I knew this one converged. So by the limit comparison, I should put this up here, by the limit comparison, therefore, the original series converges. All right. Now let's look at the other one we had done. This one. So same thing. I'm going to compare this one to sum n equals 2 to infinity of 1 over n. Remember, because we said this looked a lot like n cubed over n to the 4th. All right, I know that this diverges. So I'm going to run the limit as n goes to infinity of the original sequence in there over the one we're comparing it to. Bring that n up to the top. N to the 4th over n to the 4th minus 1. And now let's do L'Hopital. So L'Hopital, because we have infinity over infinity. And so we get 4n cubed over 4n cubed again, which is 1, which is a positive constant. Therefore, by the limit comparison, we have that this does whatever that does, so that thing diverges. Okay, now remember that one that was a little weird, kind of tricky? We had that plus in there and it kind of made us have to come in here and do that 2n. Check this out. Let's see if we can do this one now with this. So when we do this, we're going to compare this to, we're doing limit comparison. So we're going to compare it to 1 over n, which is divergent. Set up the limit. I know I'm working fast here, but set up this limit over the other one. Flip the other one up. So when I flip it up, it just becomes n to the 4th. And then again, L'Hopital one time. Because this is a plus 1, there's really not a huge difference between the last problem. It's just a minus 1. Still get 4n cubed over 4n cubed, which is 1 positive constant. Therefore, this series diverges. Okay, just like we did before. I think you would agree that's a lot easier than what we did. So you might be like, oh, okay, well, let's just, you always use the limit comparison. I get it. I mean, it's tempting. Okay. Here's a problem that might steer you into another direction or show you that there are some limitations. Okay, so all right, so let's look at this one. Natural log of n over n squared. So you're like, okay, you know, you run through, is it geometric? No. Is it harmonic? No. Is it telescopic? No. Do I want to integrate that? I could. It'd probably be an integration by parts, but I could try and integrate this. But let me see if I can compare it to something. I don't know, I'm going to try and kind of make a guess here. Maybe I can compare it to 1 over n squared, because really maybe that natural log of n isn't really that much of a factor. Let me try this. So I'm going to do the limit comparison. Oh, by the way, this is a p series. P is 2. which is greater than 1. So this is convergent. All right, so we know that's a convergent series, so I'm comparing it. I don't need any inequalities. I just need to set up the ratio, natural log n over n squared over 1 over n squared. And when you flip, bring that up, you get limit n goes to infinity. The n squareds cancel, you just get natural log of n. And as you let n go to infinity, that goes to infinity. And so this test fails. Remember, you have to have a positive constant. Infinity is not a constant, it keeps going forever. So the test fails. So maybe we picked the wrong thing to compare it to. Maybe we should have done, maybe, I don't know, something else. We can try something else. Why don't we do a different comparison? Maybe we compare it to 1 over n, which is divergent. Okay, how would that change this? Limit n goes to infinity. Natural log n over n squared over 1 over n. And so now when we do this, we flip up. Okay, this n comes up, right here, and then cancels one of those. So we should just get natural log n over n. That's infinity over infinity. So we go L'Hopital on that. 1 over n over 1, and that goes to 0. But 0 is not a positive constant, so it fails again. I don't know, maybe try something else. N cubed, square root of n, I don't know, we could try different things, but it's looking like this limit comparison is not working very well for this. So this can be done with integral test. I just wanted to show this example to show that, you know what, sometimes, because people get they fall in love with the limit comparison test, and then they get to a problem like this. They're like, oh, what do I do? I was counting on the limit comparison. Well, that doesn't always work. So, all right. I think that's it. Yeah, that is it for the notes here for 8.3. Good.